Now it's time to finally execute our darknet binary that lives in root content darknet. To create weights files in the darknet backup folder, after hundreds of iterations of forward and backward propagation of batches of images from the COCO dataset through a YOLOv3 convolutional neural network, execute this command. Exclamation point, reference to the darknet binary, detector, train, reference to the COCO data configuration file, reference to the YOLOv3 configuration file, and a reference to the base set of weights for a YOLOv3 convolutional neural network based on the ImageNet dataset, and include the flag don't show. Weights files will appear in the backup folder after 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000, 2000, 3000 iterations of forward and backward propagation. You can use the resulting YOLOv3_last.weights, YOLOv3_1000.weights, 2000.weights, 3000.weights in lieu of this base weights file, darknet53.com.74, using YOLOv3_3000.weights will allow you to continue training from a weights file corresponding to partial training. So let's go ahead and execute this darknet binary as our ultimate test to see whether we've properly set up all of the background files and dataset files required for generating weights files. First is a listing of what all of the 106 layers of a YOLOv3 convolutional neural network do. And here's a little bit of specification of some hyperparameters. And here is the output that I am used to that indicates successful beginning of training of a YOLOv3 convolutional neural network on the 2014 COCO dataset. So, after watching this for a while, you will notice that here is an index corresponding to batches. So each one of these paragraphs of output corresponds to one batch of images that are forward propagated and backward propagated through this YOLOv3 convolutional neural network that is being trained. And over time, we will see this average loss drop. Sometimes it will go up just a little bit. I think that might have to do with overcompensating in adjusting weights during each of the back propagation phases. So these lines in the paragraph corresponding to the batch of image, each line corresponds to one of the 16 subdivisions for that batch of images, and one of the 3 loss calculation or cost calculation layers in the YOLOv3 convolutional neural network. So there are 3 output lines corresponding to 1 subdivision and 3 cost output layers in the YOLO version 3 CNN, for a total of 16 times 3 or 48 lines per paragraph or per batch of images from the 2014 COCO dataset. All right, so I'm noticing that after forward and backward propagations of COCO training images, we have a batch forward and propagation time of about 4.5 seconds. Here it's down to 4 seconds. Here it's 9 seconds. So let's watch that for a little while. Ultimately, we can use the average time per batch or per iteration of forward and backward propagation to estimate the amount of time it will take to fully train this YOLO version 3 convolutional neural network on the 80 class 2014 COCO dataset. So we have 30 or so iterations performed thus far. So let's start taking these times and finding the average. All right, so here is 7.3 seconds. This is 7.5 seconds. This is 7.1 seconds. This is 7.5 seconds. An 8.2 second iteration, an 8.6 second iteration, 7.4, 7.7, 6.6, and 7.8. Okay, and here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 iteration times. I think that's a good start. So we are looking at an average time for forward propagation and backward propagation of one batch of training images from the 2014 COCO dataset of about 7.6 seconds. All right, so now let's see about an estimate of how long 2,000 iterations of forward and backward propagation of batches of 64 images each, 2,000 iterations per class, how long that will take for our 80 class COCO dataset. So we're looking at 80 classes times 2,000 iterations per class times about 7.6 seconds per iteration, which gives us a need for 1.3 million seconds to complete training of a YOLO version 3 convolutional neural network on the 2014 COCO dataset using Google Colaboratory. Google Colaboratory, by the way, is about 30 times faster in terms of forward propagation than my local Windows 10 PC. So converting this number of seconds into minutes, hours, days, and weeks, this is 21,000 minutes, 340 hours, and 14 days and 2 weeks. So if this Google Colaboratory Jupyter Notebook could run 24/7, it would take 2 weeks of computational time to fully train this YOLO version 3 convolutional neural network on the 2014 COCO dataset. Two things about that. First, the batch processing time, the time per iteration, varies depending on how many users are using the Google Colaboratory servers. Last night, when I was doing prep for this video, it seemed to be taking maybe 25-30 seconds per iteration, which would be 4 times as long. The second thing to consider is that Google Colaboratory automatically times out your work if the interface with your browser doesn't sense any activity after 90 minutes. I personally have developed a script to have Python use the Windows 10 API and click this clear output button. Eventually, this Jupyter Notebook will have that timing out problem. Given how much output is going into this code cell, there will also be an overload of the memory associated with that code cell. So clearing this output is important in both keeping the Google Colab notebook active and freeing up memory for the output of training a YOLO version 3 CNN. And another thing to consider is that if you run this training process, including the clearing of output for 12 hours consecutively, then Google Colab will at least briefly shut you down. And I haven't reached that point personally, but I have heard of that happening. And for that, I'm not sure what the wait time is between training sessions. So I guess in summary regarding time, you're looking at 2 weeks of continuous consecutive computation time. But you have to factor in the wait time between training sessions, and also maybe having to revert to the waits file corresponding to up to 1,000 iterations before the iteration that you're on, due to Google Colab shutting down while you're training, but near the end of your, I guess, millennium of iterations. So that would add, I don't know, maybe another week of continuous computational time, plus all the mental energy and time that you're expending to keep the training process going. So 2 to 3 weeks, that's pretty substantial, and this involves the state-of-the-art GPU-enabled servers on that Google owns. All right. So here, we started with a loss that I'm trying to find. We started with an average loss of about 1650, and let's clear this output. And here is a loss of half of that. So it seems that this training is successful on the 2014 COCO dataset, and we're almost 100 iterations in. And each iteration is now taking actually less than 7.5 seconds. It's about 5.5 seconds now. That could be a simplification or a streamlining internally in the training, or it could be that GPU resources are freeing up on the Google server. So I feel ready to end this training session and briefly test out the training sessions for the Pascal VOC 2007 and 2012 datasets and my custom dataset of oak leaf images. Okay, so let's start up this execution of the darknet binary. Again, a presentation of the architecture of the YOLO version 3 convolutional neural network we're using. A little bit about hyperparameters here. And here again is our first paragraph corresponding to the output of 3 layers for each of 16 subdivisions associated with one batch of 64 training images corresponding to the Pascal VOC 2007 and 2012 datasets. And we have early on an average loss of about 1700. That's comparable. We have a batch iteration time of about 6.6 seconds. And given that this is across iterations and across training programs, it seems that this might be variable based on Google's processing resources. But I'm going to keep it at 7.5 seconds average iteration time, because I know that the iteration time can be fairly high. So to get an estimate here of the computation time for 20 classes associated with the Pascal VOC 2007 and 2012 datasets, we're looking at 20 classes times 2,000 iterations of forward and backward propagation of batches of training images through this YOLO version 3 convolutional neural network. And let's say again that each iteration takes 7.5 seconds. That's we need 300,000 seconds to complete 20 times 2,000 iterations of forward and backward propagation to adequately train this YOLO version 3 CNN on 20 classes of objects. And this corresponds to 5,000 minutes. Reminds me of a song. Or 84 hours, or 4 days. And if you again factor in your overhead time to reboot your YOLOv3 training notebook, then I could see about a week of computational time. So for Coco, we were looking at maybe 2 to 3 weeks of computation time at best. And here we're looking at about 1 week for about a quarter of the classes. So here we've dropped in average loss from 1,700 to about 1,000, and this seems to be working as well. So let's clear the output here and pause our training program on the Pascal VOC 2007 and 2012 datasets. That definitely seemed to succeed. And finally, let us try to execute this darknet binary of ours to train a YOLO version 3 convolutional neural network on my custom oak leaf dataset by executing this command. Here we have a presentation of the architecture of our YOLO convolutional neural network again, a presentation of a few hyperparameters, and here again is our paragraphs corresponding to batches of forward and backward propagation, batches of training images associated with the oak leaf dataset that are forward and backward propagated through the YOLO CNN. Each line again corresponds to one subdivision of the 16, corresponding with 4 images, and one of the 3 cost calculation layers in the architecture, for a total of 48 lines in each paragraph corresponding to one batch of training images and iteration of forward and backward propagation of that batch of training images. So here we have an average loss of about 2,400, and then a few iterations later, it really hasn't changed all that much yet. So in the meantime, let us do a quick calculation of probably how much time this calculation will take. This full training, I mean. So we're looking at one class here, and we're wanting at least 4,000 iterations per Alexei AB's recommendation. And let's say 7.5 seconds again per iteration. This is doing better right now, but it could be worse tonight. And then we need 30,000 seconds to do a full training on our oak leaf identifier, our detector, which is 500 minutes, which is 9 hours. So it seems that, at least right now, we can complete training of a YOLOv3 convolutional neural network and receive an output weights file for forward propagating any image of an oak leaf or oak leaves. We need 9 hours to do the training, which is under our 12-hour limit. So as long as we have an API call to do this output clearing, then we should be able to generate a weights file for an oak leaf detector within one waking period. But it still takes many hours. And this is one class. What if I want to identify all classes of tree leaves in Virginia? That seems like a daunting goal. I would learn a lot in the process, though. All right, so let's check the cost again. So here we have an average loss of, wait for the most recent one, about 1,600. And that came down from this is a lot of output, I gotta admit. This came down from 2,400 to 1,600 in how many iterations? An 800 drop in average loss. Over 40 iterations. So perhaps this data set is more diverse. Or perhaps it's harder to quickly minimize loss and adjust weights when you're iterating over one or two batches corresponding to an entire data set. So it may be that developing more oak leaf training images and label files might speed this training process. Well, I certainly don't want to restrict the diversity of my oak leaf dataset. But perhaps more images will provide more examples of species and maybe some more uniformity among oak leaves as a genus. So this training seems to be successful as well. So let's clear the output. Stop our detector for now. All right, so here again, we have 3 commands that call a darknet binary and root content darknet. And based on a lot of background dataset files and configuration files and an initial weights file, train a YOLOv3 convolutional neural network on one of 3 very different datasets.